Welcome back. Today we're going to talk about Markov chains. Markov chains are the simplest stochastic process. They're a discrete process in which the future state of a system depends only on the current state. There's tons of applications in physics and biology and computer science and finance. So suppose that you're playing a soccer match and you are set up so that if you win one match, then your probability of winning the next match is, say, 60% because you're boosted from winning. You feel better. And that means that you have a 40% chance of losing the next match. And let's say that if you lose the match, it makes you feel just terrible. And so you only have, say, a 25% chance of winning the next match. Which means that you have a 75% chance of losing. So losing is like attracting more losses. So how can I, if this is always true from any one match to the next, how can I determine sort of my future chances of winning or losing? How many games will I win in the long run? Well, in 3 games, if I win, let's say, if I win now, 3 matches from now, how will I do? What's my probability of winning? Well, let me set L to the LK, let's call it. LK is the percent chance of losing the kth match. The loss chance at the kth step. And WK can be the win chance at the kth step. The probability of winning the kth match. So what I'm looking for if I want 3 matches later is I want a vector that in the first coordinate, let's say, is the probability of winning the 3rd match and the probability of losing the 3rd match in the 2nd coordinate. This should be a probability vector in the sense that those 2 things should be positive and add up to, say, 1. Probabilities are going to take values between 0 and 1. So first, observe that there's no ties in this setup, so that the probability of losing plus the probability of winning the kth match should be 1. 100% will be 1. 0% will be 0. 25% will be 1/4. The second thing that we need to notice is that the probability of winning the k plus first match will depend on the kth match. So if we won, then there's a 60% chance. And if we lost the kth match, and this is a misprint, it should say 0.25 there, then there's a 25% chance of winning. So we'll just multiply those in and add them up. Similarly, again, there's going to be a misprint here, but losing the k plus first match, well, you've got a 40% chance of doing that if you win, and you've got a 75% chance of doing that if you lost. So the 0.75 and 0.25 should be swapped here. And I think I got it right in the matrix that we're going to see. So the point is that I can express WK plus 1 and LK plus 1 in terms of WK and LK. It's just the 2x2 matrix, 0.6, 0.25, now good, we got it swapped back, 0.4, 0.75, times the vector WK, LK. So if I want to know how I do later, it depends on how I did earlier. Let's say that I don't know, lost the first match. Well, then the probability of winning the first match is 0, and the probability of losing the first match is 1, because I lost. Well, what does that mean for the 3rd match, for example? Well, W1 is 0, and L1 is 1. And I can express W2 and L2 in terms of this matrix times that vector. So W2, L2 is 0.6, 0.4, 0.25, 0.75 times 0, 1. And that's just the 2nd column. So that makes perfect sense. It's exactly what we had set up. The probability of losing if I lost was 75%. Where things get interesting is the third game. Because now it's given to me by multiplying that same transition matrix by the new probability vector 0.25, 0.75. And the numbers come out to be about 33% chance of winning, about 66% chance of losing. Let's go one more stage, see what happens. Probability of winning the fourth match and the probability of losing the fourth match are determined by multiplying this matrix times the probability vector from the third match, so that's 0.3375, 0.6625. Multiplying this out, you just crunch the numbers and you find about 36.8% chance of winning the fourth match, given that you'd lost the first one, and about 63% chance of losing it. You can do this as long as you want. The chain of vectors that you build in this way will converge. In the long run, they converge to somewhere in the neighborhood of 38%. So your win probability in general, in the long run, is about 38%, and your loss probability is the complement of that. It's 1 minus 38, so I guess 62. 62% chance. So in the long run, you should be losing 62% of games and winning 38% of games, given that you lost the first one. That's how to interpret that. The really striking fact is that if you do the same computation, having started at 1-0, having won your first game, it doesn't matter. They'll converge to the same win and loss probabilities as k gets very large. As you keep on iterating this system, whatever vector you started with will converge toward this 38%, 62% ratio. So let's make a definition. I need to define probability vector. So a probability vector is a vector in Rn, where n is some number that's at least 1. Let's call that vector v1 through vn. And I need to insist that all of the entries in the vector are probabilities. So what does that mean? Well, not only are they probabilities, but they add up to 1. All possibilities are accounted for. So they add up to 1, and they're all non-negative. That's the whole point. That's what a probability vector is going to be. So before, when we had 0.25, 0.75, there's 25% chance of losing and 75% chance of winning. That vector was a probability vector. Now, if you have any vector that has all positive entries, you can scale it to become a probability vector in a unique way. There's only one way to do this. And so I'd like to show you how. You should just divide by the sum of the entries. Of course, if you're already a probability vector, then the sum of the entries is 1, so that won't change anything. But if you're not a probability vector and you divide by the sum of the entries, you'll get a vector whose entries now sum to 1, and if they were all non-negative, well then, now you have a probability vector. So for example, if I have the vector 1, 3, not a probability vector, and I divide out by the sum of 3 and 1, divide by 4, 1/4, 3/4 is what I get, and lo and behold, this is a vector of probabilities. You can always do this with any vector that has non-negative coefficient entries, and you can do it in a unique way. Now we're ready to define Markov chains. So a Markov chain is what we just saw an example of with the soccer matches. It's a chain, if you like, of vectors. These are the probability vectors. So this is a chain of probability vectors, say v upper 1, v upper 2, v upper 3 up to the upper k, and it just keeps going forever. The product of an iterative system. These are all probability vectors, and for every k, they're related by a matrix, which is going to be called a transition matrix. So vk is can be written as some matrix t times vk minus 1 for each k. It's the same t every time. You just iterate powers of this matrix. And that matrix T is going to be special. All the columns of T are probability vectors. That's going to be called a Markov matrix or a transition matrix for Markov chain. The chain is the sequence of vectors. The transition matrix is how you get from one to the next. So in the last example, the transition matrix was that 2x2 matrix, and the sequence of probabilities, win-loss probabilities, was the Markov chain. So if I have a transition matrix, let's say the entries are Tij's, so the Tij in the ith row and the jth column. Because the T is a Markov matrix, the columns are probability vectors, and so all of the entries are in between 0 and 1 first. And second, well, those columns sum up to exactly 1. So for each j, t1j plus t2j, and so on, plus tnj, if t is n by n, adds up to 1. Because the columns were probability vectors. So we're going to make use of that equation in just a minute. So Tij is the probability of transitioning from state j to state I. It's important that we keep track of which one's which. It's really common mistake to think that Tij is sending you from state I to state j. You have to go backwards, so keep that in mind. You're going from state j, from the Tij, to the state I, j to I. So we're interested in the long-term behavior of systems like this, of these iterative systems. Well, they don't always converge. But there's a relatively mild condition we can impose that will guarantee that they do converge. And so I need to define that condition. This condition, you shouldn't confuse. We're going to have to overload our language a little bit. So we're going to say that the matrix is called regular. If some power of that matrix has all positive entries. Now, I don't want you to confuse this notion of regularity with the regularity that involves LU decompositions, having an LU decomposition without any row swaps. It's a totally different concept. It's utterly different. It's not at all the same. It's unrelated in every way. But if there's some power of the matrix that has all positive entries, and none of the entries are 0 in, say, the 15th power of the matrix, then I'm going to call the original matrix, T, that transition matrix, I'm going to call it regular. And I just really want to emphasize that this is not anything to do with LU decompositions. It's a brand new concept. So the word regular is terribly overloaded in math. It's used in just a million different contexts, and you have to be careful what someone is talking about. This is called semantic overload. So let's continue thinking about regularity. So the point is that the entries of the kth power of t, let's say I take k equals 5, and the entries of the 5th power of t, are the probabilities, say the ij entry of t to the k, is the probability of transitioning from j to I in exactly k-step. You call it a k-step transition probability. Okay, so let's say t to the k is Sij, for some entries S. Then Sij, that's the probability of moving from the jth state, to transition from the jth state to the ith state in precisely k moves. So we're going to see some examples that will make that a little bit more clear, I hope, shortly. But the point is that a matrix, a transition matrix, is regular if there's some k that's large enough, if for some large enough k, you can go from any state to any other state with non-zero probability in exactly k moves. So again, regularity says for some perhaps large number k, there is a chance, doesn't have to be a large chance, just some positive probability that you can go from state I to state j in precisely k moves, in exactly k steps, for every I and every j. Now, the big theorem about these Markov chains is that this condition, which is not especially strict, guarantees convergence of the Markov chains. So if T is a regular transition matrix, meaning some power of it has all positive entries, then if you look at the one eigenspace of your matrix, well, what is a one eigenvector? That's a vector that when you apply T to it, it doesn't change, right? You get 1 times it, you get the vector back. So the one eigenspace has dimension exactly 1. There's one eigenvector. There's a unique fixed point, if you like, a vector that is not changed by T. And not only that, but that vector, well, that eigenspace, the entries all have the same sign. In particular, you can find a one eigenvector, a fixed point, which is also called a steady state vector for the system, that has all positive entries, and in particular you can scale it to be a probability vector. So there's a unique probability vector that's fixed by T. And, even better, the Markov chain, no matter where you start your Markov chain, any Markov chain with this transition matrix will converge as k goes to infinity to that steady state vector, that fixed point for T, that probability vector. Doesn't matter, no matter where you start, any starting point at all, any Markov chain with this matrix will converge to that fixed point. So because there's only one way to, so because the dimension of this eigenspace is 1, and because there's only one way to scale a vector to be a probability vector, as long as it had positive entries, there's really nothing you can do. There's only one possible place that all these things are converging to. So now let's consider the same example that we had before. I have this win-loss matrix that we had with the soccer matches. T was 0.6, 0.25, 0.4, 0.75. And let's say state 1 is winning and state 2 is losing. So T11 is the probability of transitioning from state 1 to state 1, the probability of winning if you already won, the chance of going from win to win. And we said that was 60%. And T21 is the chance of going from state 1 to state 2, the chance of losing after you've won, and that was 40%. T12 is the chance of going from 2 to 1, the chance of moving from a loss to a win. We said that was 25%, because you felt bad, I think. And the chance of going from a loss to a loss was, well, 75%. There was no other choice. There were no ties in this setup. If we'd had ties, we'd need to include, it'd be a 3x3 matrix. So if you look at this particular matrix, you can observe first that it's regular. How do I know it's regular? How do I know that some power has positive entries? Well, how about k equals 1? It's regular because it already has all positive entries. So the one eigenspace exists. In fact, you can compute easily that the two eigenvalues are 1 and 7/20. And you can find a one eigenvector also very easily. and it's 5/8 1 is the quickest one I could find. And I can scale that to be a probability vector by dividing by 1 plus 5/8, which is 13/8. And so you're going to get 5/13 and 8/13 are your probabilities. Those are the percentages that we found after a few steps. Point is that as k goes to infinity, the kth state in the chain will converge to be very close to 5/13, 8/13. So this thing, again, is called a steady state vector. And the point is that in the long run, as k gets very large, the probability of a win is about 5 out of 13. You should expect to win about 5 out of every 13 games in the long run as k gets very large, regardless of whether you won the first one or lost the first one. So maybe that seemed a little bit contrived. Let's consider the following situation. Suppose I have a graph on 3 vertices, and I put a bug on the graph. And the bug, if it's on node 1, there's a 10% chance it'll stay on node 1 for that step. A 10% chance it'll move to node 3, and an 80% chance it'll move to node 2. Similarly, if I put it on node 3, there's no chance it'll move to stay where it is, and no chance it'll move to node 1, but a 100% chance it always wants to go to 2. Grass is always cleaner. And if I put it on node 2, then there's a 25% chance it'll stay, a 25% chance it'll move to node 3, and 50% chance it moves to node 1. So I put this in a little bit of a table. So instead of the 10% chance, I write 0.1 of transitioning from 1 to 1. That's fine. 80% chance of going from 1 to 2, 10% chance of moving from 1 to 3, and so on. So I just filled in these columns. You can imagine that these are 3 locations in the city, and you're counting where taxi cabs are likely to go, and asking yourself, in the long run, how are my taxi cabs going to be distributed? So Tij, the entry of the transition matrix that I plan to build, is the probability of moving from node j to node I. So the first column is just going to be this first column that we have, and I'm going to write them as fractions to make my calculations easier. So just put 1/10, 8/10, 1/10 in the first column, 1/2, 1/4, 1/4 in the second column, and 0 and 0 in the third. Notice that all the columns add up to 1, and they're all numbers in between 0 and 1. So you can check pretty easily that this matrix is regular. In fact, if you just square the matrix, you'll find that it has no 0 entries. They're all positive. Which means that that theorem gives you a guaranteed 1 eigenspace of dimension 1, a probability vector that's a fixed point, a steady state vector. Now, we could have just looked for a 1 eigenspace, that wouldn't have hurt, but if the matrix was very large, it might be nice to know that it was regular. So you can compute the 1 eigenspace. It's spanned by 20/11, 36/11, and 1. And if you want, you can scale that to be a probability vector. You'll have to divide by 11/67, or rather multiply by 11/67, divide by 67/11, and well, you'll get 20/67, 36/67, and 11/67. What does that say? How do I interpret this? Well, 20/67 is about 29.8%. 36/67 is about 53.7%, and 11/67 is about 16.4%, which tells you that in the long run, my bug is going to be spending 53% of his time on node 2, and very little time on node 3, because, well, he always shunts over from node 3. Or if you like, if I had a ton of taxi cabs at these 3 locations in the city, then no matter how I distributed them to start with, they're going to end up about 53% of them in zone 2. Another reasonable thing to try to do is to think about something called a random walk on a graph. So a graph is just a collection of dots and edges, nodes and edges between the nodes. So a random walk, assume that you're on node I, and that there's a probability, an equal probability of moving to any one of the nodes that are connected to node I. So if you're on node 1, then there's 33% chance of moving to node 2, 33% chance to node 4, and 33% chance to node 3. 33 and a third. So the question to ask is, after k steps, suppose you started on node 1, what's the probability of being on the ith node after you'd moved k steps? If k is large enough, and the transition matrix for the Markov chain that we're going to build is regular, we'll be guaranteed that it didn't matter where you started. Your probabilities will converge to some limiting value, which will be a steady state vector. So, well, how do I build this T? Well, how do I transition from node 1? Well, I can't stay there. I have to go to either node 2, 3, or 4, and I have equal probability of doing each 1/3 of each. From node 2, I can only either go to either 1 or 4 because it's not connected to node 3. Similarly, for node 3, I can only either go to 1 or 4 with equal chance. And from node 4, it can't stay where it is, but it could go to 1, 2, or 3 with equal chance. So this is also sometimes called the drunkard's walk, and you sort of want to compute the expected time before we get someplace. We're not going to go that deep into this. So it turns out that this matrix is regular, and it has a 1 eigenvector, given by that formula, 1, 2/3, 2/3, 1, which, if you want, you can scale into a probability vector, 3/10, 2/10, 2/10, and 3/10, which you interpret as saying that for large k, after a ton of steps, after 10,000 moves, didn't matter where you started, after 10,000 moves, there's a 30% chance, approximately, that you will land on node 1. There's a 30% chance of being on node 4, a 20% chance of being on node 2, and a 20% chance of being on node 3. Which kind of makes sense, given that there's 2 edges coming into node 2 and node 3, 3 coming into node 1 and 4. Now, there are 2 caveats that I need to make clear here. Regularity is not all you need. So first, I guess I should say that a steady state vector can exist for a matrix that is not regular. So if your matrix is not regular, that doesn't mean the eigenspace doesn't have the one eigenspace doesn't exist, or even that it doesn't have a probability vector in it. For example, this matrix, the identity matrix, definitely is not regular. There's no power of this matrix you can take that won't have zeros in it because it's the identity matrix. All the powers are it. It won't change. So no power you take of this thing will have all non-zero entries. Nevertheless, it has a couple of independent steady-state probability vectors. I hope you can think of some. In fact, every vector is fixed by this. So regular implies existence of steady-state probability vectors, but not the other way around. Second caveat. Just because you have a transition matrix that's a Markov matrix, meaning its columns are probability vectors, does not mean you have a steady-state vector. Existence of steady-state vectors, which is going to be the place you expect to converge to, that is guaranteed by the theorem. So we've got a theorem that says if I have a regular transition matrix, some power has all positive entries, then that guarantees me the existence of a steady-state vector, but not every transition matrix is regular, and not every transition matrix has a steady-state vector. So the easy example is this one, 0, 1, 1, 0. So this thing is not regular. No power you take of it is ever going to have all positive entries. And even more, if you try to compute the eigenvalues, that won't be very hard. There are I and minus I. There's only complex eigenvalues. There's no steady-state vector. There's no one eigenspace. No fixed point. even though it's a Markov matrix. So the last thing that I want to talk about is the Google algorithm, the algorithm they use to rank pages. So we're going to make a model internet. There's only 4 websites on this internet, and page 1 has a link to page 2. Page 2 has a link to page 3, but page 3 does not have a link back to page 2, if that makes sense. So 1 and 4 link to each other. I'm going to set n sub j to be the number of outgoing links on page j. So n sub 1 should be the number of outgoing links from page 1. 1 is linking to 3 different places to 2, 3, and 4. We're going to use that number to try to help determine the importance of the page. So the plan is that I want to assign some kind of ranking to the page, because in what order should I list my search results? How important is the page that I'm looking at? That should be related to how many other people are linking to it, because every time I link to a page, it's like I'm voting for how important that page is. So let me set xj to be the rank of the page j. So I want to determine a ranking for page 1, for page 2, page 3, and page 4, so that I can determine what order to display the search results. So the plan is a brilliant plan, a Brin and Page, is that I should set x1, the rank of page 1 should be, well, it should be the rank of page 3 divided by, that's the importance of page 3, divided by the number of votes that page 3 is casting, plus the number of, plus the importance of page 4 divided by the number of votes that page 4 is casting. 3 and 4 are the only 2 nodes that are pages that are linking to page 1, so I should just add up like a normalized vote for page 1 from all the places they're linking to it. So x3 is the importance of page 3, and n3 is how many votes page 3 is casting for importance of of all pages everywhere. So if I normalize it down like that, I can certainly get an equation. So 3 and 4, again, are the only 2 people that are linking to page 1. They're the only ones voting for it. So I want to set the importance of page 1 to be the importance of page 3 divided by how many votes 3 is casting, plus the importance of 4 divided by how many votes 4 is casting. So let's just really quickly compute what are the n sub j. So n sub 1, well, that is the number of outgoing links from page 1, and that is one that they're going to 2, 3, and 4. 2 is only linking to 4 and 3, so that's got size 2. And 3, page 3 is casting only 1 vote for page 1. And page 4 is casting 2 votes, 1 for 1 and 1 for 3. So there's 2 outgoing arrows from node 4. So we see x1 is going to be x3 divided by 1 plus x4 divided by 2. That should read x2. x2 is, well, who's pointing into 2? Just page 1. So it's just going to be x1, and x1 is pointing to 3 places, so we'll divide by 3. x3, well, there are 3 things pointing to it, x1, x2, and x4, or rather page 1, page 2, and page 4. And finally, x4 is being pointed to by 1 and 2. All right, so I can stick all this stuff in a matrix. This really looks like a matrix vector equation, doesn't it? And if you set that, this is a system of linear equations. And what you're trying to solve is that this matrix, this 4x4, and that bottom entry should say 1/3. Bottom left entry is 1/3. Now this matrix times the vector x1, x2, x3, x4 is equal to x1, x2, x3, x4. In other words, and look, observe that this is a Markov matrix. The columns are indeed probability vectors. You're looking for a steady state vector for a Markov chain. You want a 1 eigenvector, and you'd like it to be a vector of probabilities if you can make it be, because then you'll have an easy way of ranking. The things with the largest probabilities will be the best pages, the most important pages. So you can find a 1 eigenvector for this matrix. It's 2, 2/3, 3/2, 1. And if you want, you can scale that to be a probability vector. But the point is that the largest number on here is the most important page, and the smallest number is the least important page, according to this particular ranking algorithm. So you can scale this. Those numbers are basically illegible. In short, you will get about 38.7% chance of landing on page 1 after a bunch of clicks. 12.9, 29%, and 19 I think it's 4%. So that number is the biggest, so I'll rank that page as the best page. So page 1 is the most important page. Page 3 is the second most important page. Page 4 is the third most important page. And page 2 is the lamest page. Only one page links to it. Okay, so this matrix you can think of as a transition matrix for doing a random walk on this graph that is the internet. So the point is I'm going to model the entire internet as a directed graph. I'll assume that I'm web surfing. I'm randomly clicking on some link that's on the site. So I'll have an arrow out to every other site that I linked. So each site will have an arrow out to a site that it links to. And the question is, after I randomly click a bunch of links, where do I end up? Well, I should end up at the most central pages of the internet, the most influential pages somehow. Well, that's fine, but how do I know this matrix actually, how do I know I'll end up anywhere? Why should I converge to some steady state vector? How do I even know that there is a steady state vector? I've got some zeros in this matrix, and it turns out that this one with this 4 nodes is regular, but I mean, what if there's certainly pages on the internet that are dead ends that I get linked to but never link out? My server could end up there. These states, by the way, are called absorbing states, those dead end pages. And they're death to regularity. So, well, the solution that Brin and Page came up with is a pretty clever solution. Let's just force our transition matrix to always have positive entries. Then every power of it will have positive entries. Because there's no negatives. Nothing can cancel out. So here's what we'll do. Let's just make all the entries of this matrix be positive. Well, how? I want to do it in a reasonable way that models internet user behavior somehow. How about this? Let's take our transition matrix, let's call it A, and we'll replace it by some multiple of A. In this case, let's choose 85% A, and 15% chance of, let's put all 1/4. Why 1/4? Well, that's the number of pages in my model internet. So let n be the size of my model of the World Wide Web, with counts of how many places each site is linking to. If n is a billion, then fine. So the story is that you are modeling a surfer who has an equal chance of clicking just completely randomly on one of the pages, or one of the links on the pages that he's on. And also a 15% chance of not doing that at all, but just opening an utterly random web page to somewhere else on the internet. So you can never get stuck. You'll always jump out of dead ends. I have a chance of jumping out of dead ends. This algorithm is what Google is using with a very large matrix, more or less.